With regards to the file itself, it's a Google Colab notebook. So ideally, you can open it on the Google Colab. So just open up Google Colab in your website or your browser, and you should be able to upload that file if it's not able to open on your local machine.
Okay, I will send it in another link right now.
All right, sounds great. To answer Mo Ragag, it's better if you open it on the Google Colab link, because as a PDF, it'll be a bit difficult to follow along. In this file, we're actually going to do a little bit of Python coding. So ideally, it would be best if you could open it on your laptop on the Google Colab site. All right. On that note, I suppose we can begin. For all of those who just recently joined, we have uploaded our file for today. And I believe tech support will be sending a Google Colab link later on in the chat, so that once we fully get into the session, we can follow along with the examples I'll be showing on the screen. Okay, to start things off, just a quick introduction about myself. Hi, everybody. My name is Ma Althea Retig, and I am a bachelor student in my 4th year of computer science, specializing in AI. And additionally, I am one of my recent achievements is being a TEDx speaker. And I wanted to share like a couple of lessons that I learned throughout my bachelor's and throughout my courses with relation to AI and data science, which brings us to today's session. So for the session of today, there is a bit of a prerequisite that I hope everybody has, in which sense, like, I hope everyone has a basic understanding of Python, because it's going to be the main language that we'll be working with for this session. And additionally, I hope you guys are able to navigate the Google Colab notebook as well, because that is the environment where we're going to run the code that we'll see later on. Right. So for today, we're going to sort of have a beginner's tutorial or beginner's session on how to evaluate and improve on machine learning models. So I'm sure all of us are aware of the amount of new machine learning models that are popping up, the amount of large language models, LLMs, generative AI models. So with all of these different models, how can we decide, especially on the programming side, how can we decide which models are good to use? Which models can help us achieve the aim of our project? So we do that, of course, by evaluating our models. Now, there are a couple of ways that you can do that, and we're going to dive into that right now. So first things first, our evaluation methods. And for evaluation methods, we have performance metrics and cross-validation, which are the two things that we're going to be focusing on in the technical part of this tutorial. So first things first, I want to bring your attention to the performance matrix. We have 4 things that we want to focus on. So that's primarily the accuracy, the precision, the recall, and the F1 score of our models. Now, these are the 4 most basic performance metrics that we can use. And especially in terms of accuracy, it's widely used within the industry. But of course, there are many other performance metrics that we can use to sort of judge how accurate a model is, depending on the use case. So for example, generally for classification use cases, when we want to classify if the output is one thing or another, we can use accuracy. But for a little bit more nuanced use cases like image segmentation or image recognition, for things like that, we can use what is called intersection over union. So it's a sort of another way to describe the accuracy of that model within that use case. For now, though, since we're focusing on the basics of evaluation, we're going to focus on these four that are being shown on the screen right now. And the next thing is cross-validation. So this evaluation method is a sort of way to test the performance of our model on an existing data set that we have. And in order to get less biased results, we do cross-validation, in which we go through each and every single part of the data set and make sure that our model has been trained on every single part of that data set. Now, the usual way we achieve the accuracy score of a model is when we section a part of our data set to keep it for training and another part of our data set to keep it for testing. So usually when we go through that traditional division, that means that one section of the data set will not be given to the model for training. So we sort of have a limited data set for training. But when we do cross-validation, we can go through we can go through every record in our data set that allows us to have a less biased output, because the machine was able to learn through the entire data set that we have, rather than just one section of it. So we're going to be focusing on the k-fold cross-validation process for this specific tutorial. Now, I did mention that there are two things that we're going to address today, which is evaluation and improvement. So we've just gone through like a quick overview of our evaluation methods. Now we're going on to our improvement methods. So these are a couple of the methods that we can use to improve on an existing machine learning model. First thing is hyperparameter tuning. Now, this includes changing the learning rate of the model or going through the other parameters that we use when building the model. We won't be focusing on this as much, but we will be showing more of a focus on the last two. However, we'll go through an overview of all of them. So we had the hyperparameter tuning, which is more on changing specific features of our model and going through iterations of them to see what changes produces the best results through our evaluation methods, such as which has the best accuracy and so on and so forth. For the second one, transfer learning. Now, this is a specific method of improvement that's great when your data set is quite limited. So basically what it does is you take an already previously trained model and you use that model and the parameters that it has onto your specific use case. So you're sort of like taking what the model has already learned from a larger data set and then using that learning into your use case, but you're going to still train it a little by giving it your data. So even though your data is limited, the performance of the model itself will still be pretty good because it learned from a previous training session. And the third one is oversampling. So this method is used in cases where you have, for example, in classification, when you have an unbalanced data set. So when one class has a larger amount of data as compared to another class. So that's usually when you'd want to oversample and sort of get the values of both classes to be the same. However, there is a sort of caveat to oversampling. It's not always recommended for all, how to say, for all use cases. Because for oversampling, like what I mentioned, we want to sort of bring the class numbers to be equal. However, that's only assuming that oversampling will make our data more representative of real life data. So you're going to have to explore your data more to see if oversampling is the right model improvement method for you. Now, the fourth one, another model improvement method, is our ensemble methods. Specifically for this tutorial, we're going to be looking into the random forest classifier ensemble method. So for ensemble methods, the whole idea of the process is taking predictions or accuracies from a bunch of smaller and weaker models and then aggregating all of those results to produce a less biased, or what is hopefully a less biased result as one model. So small models, many small models contributing to the result of one larger aggregated model. Right. So that's a quick overview of our two things today: model evaluation and model improvement. So we're going to put into practice the things that we touched upon. Specifically, for evaluation methods, we're going to be focusing on getting these performance metrics. And for cross-validation, we're going to be focusing on how to, or understanding more of how to do k-fold cross-validation. Then for model improvement, we'll go over oversampling and the code that we have for it and the libraries that are available for it, as well as the random forest classifier. So if everyone is able to access the notebook shared in the chat, do let me know. I will be going along and showing the notebook itself on my screen. So if you guys can somehow copy it as we go, then that'd be great. But ideally, the notebook should be available to you guys by now. Do let me know if you guys are able to access it. In the meanwhile, I'll just give a quick overview of what you can expect from this tutorial. So for this tutorial, we're going to be diving into a classic sample dataset, which is the Titanic dataset. So in this case study, the goal, or our goal for now, is to create and improve upon a model that classifies whether or not a person is likely to have survived or not survived the Titanic. So let's go ahead and quickly go through an overview of that. Our notebook, if you guys are able to access it, has 3 sections. So we won't be going too much into exploratory data analysis or all of the steps leading up to creating a model. However, we will be focusing more on the end part where we evaluate the models that are available to us and sort of compare their accuracies. And then later on in the third section, we will try to improve. I see on chat that they're saying the notebook is not allowing access. Let me see if I can. All right, I'm going to be sending over a link on the chat. Hopefully this one allows it to be seen. Mhm. All right, so I've sent over a link for the notebook in chat. If you guys can open it and access it, do let me know. If not, also do let me know. In the meanwhile, I'm going to be showing you guys my copy on screen. So the notebook that I have provided is a sort of fill in the blanks type of notebook. So in this activity, we're going to be going through the steps together one by one and filling in the code as we go along. If anyone can confirm that they are able to access the file on chat.
Maria, I just made
Yes.
you the host, so you can share it again on the in the chat, so it will appear for them. I'm so sorry for the delay.
Okay. All right, sure thing. Right. Okay. So I just sent the link on chat on a different account, but yes, that Google Drive link should be able to show you guys the note. Okay, that's lovely. Right. So Faris and everybody, for those who can access the notebook, what you can do is first make a copy of it. So save a copy in your Google Drive so that you can actually edit and save your edits on this notebook. All right. So while you guys are doing that, let's get started with the intro to this case study. So like I mentioned before, the whole goal of our tutorial today is to sort of see how we can evaluate this classification model. So we're going to be accessing data from a CSV file called titanic.csv. So it's going to be a very small data set just to sort of help us get through the concepts that I introduced today. So first things first that we need to do is one thing we have to keep in mind whenever we're creating and evaluating and improving machine learning models is we have to have the proper libraries for it. So as you can see here, we've listed a couple of libraries that are important for us to have, such as Numpy, Matplotlib, Pandas, and Sklearn. So for these, Numpy especially is for allowing us to be able to manipulate the data using arrays. And for Matplotlib, we can use that to sort of visualize how our data looks like. Then Pandas and Sklearn, we can use that. Pandas gives us data frames, which allows us to load in our data into our current environment. And Sklearn is, of course, the main library that we use in order to access machine learning models and our performance metrics functions. So if you are able to open the notebook, I want you to go ahead and run that. So running this particular cell makes sure that our current Colab environment has access to these necessary libraries. If I'm going a bit too fast, you guys can let me know. But in the meanwhile, we'll just continue on. And the next thing we have to do is, of course, importing the data. Now, there are multiple ways that you can import your data into a Google Colab environment. If you have your data saved with you on your local drive, you can simply upload your file here into the actual environment. But for now, we're going to clone a different repo that actually has this data set that we are looking for. So again, we run this cell and then it clones this repository. And we change into this specific folder, which has the files that we need to work on this problem. Right, now once that's done, we load in the dataset into our actual environment using the Pandas read the CSV function. So as you can see, we're now showing the features of the dataset that we're interested in looking at, specifically our label, which is whether or not these people had survived, and then a couple of features about the people related in the dataset. So for this one, again, we're using a lot of pandas from the pandas functions from the pandas library to sort of load in the dataset here and the specific columns that we want. And for this one, the values in our dataset for the gender is male and female. So that's categorical rather than numerical. However, machine learning models work best when the data that they have is numerical. So what we're doing here is sort of replacing these strings into integers. So now you can see that rather than male and female, gender has become zeros and ones. Then next, this entire steps is just introducing us to the data set itself. So we kind of want to get to know the shape of the data. So when we're referring about shape, we're talking about how many rows and how many columns are inside this data set. So it gives you a sort of overview of how your data set looks like. Now, when you're working with a machine learning problem, you would opt to do more exploratory data analysis than just what we did here. But for now, we'll keep that to the side. Right. So once we sort of are more familiar with our data set, now we want to sort of edit it in a way. So that phase is called data pre-processing. So for this one, what we want to look at is whether or not our data set has a few missing values or null values. And as you can see, using this command, the isNull.sum, it sort of adds up how many rows inside these columns have null values. So the only column with null values that we can see so far is age, which is all around 177. So that's almost 1/8 of our total data set. So that's quite a large portion of our data set to be having as blank. And since age is a numerical value, we can fill it in with using a couple of operations. So that operation that we want to use to fill in our missing values is by using the mean of the total ages. So you can run that using this command. So it shows that inside the column of this data set, we want to fill in all that's null with this value, and the value being the mean of our overall age in this column. Then after you do that, you can just check again to make sure that your null values are filled. And as you can see, there are no more null values inside our data set. Now, another data pre-processing step, which is important, especially for all machine learning model use cases, is dividing the data set into our attributes and our labels. So that's basically our features and the result that we are looking for. So we usually split it up into X and Y. The first one being X being our attributes and Y being our labels. So this is what we're looking for, which is why we have just this column inside our Y variable. Inside our X variable, we have all of the other columns excepting for this, our label, and then the name. So you can go ahead and run that. And now we're going to be diving into how k-fold cross-validation works. So like I mentioned before, when it comes to cross-validation, or just when we just want to train our data set, we usually have one section that's kept for testing, which means that the machine learning model doesn't originally get to look at that section of the data set. But the rest of the data set, it uses to look at the attributes and the corresponding labels to them. So it sort of sees like um, which features matches up with which labels. And then it uses whatever it learned during that training period to be able to predict the labels for the test section. So in the test section, the machine learning model is only shown the attributes, and they're supposed to guess the labels or the results. And then we it is up to us to be able to see how accurate their guesses are. And that's when we go into the score or the accuracy. But when it comes to k-fold, we want to avoid keeping one part of the data set as our sort of dark area for the machine learning model. So in order to avoid that, we use k-folds, where given a number of folds, we iterate through each fold, making sure that the model is exposed to all folds throughout the training process. And you can see that over here. So you can see this first one is kept for test, but in the next iteration, the second fold is kept for test. So it just goes on and on until we reach the number of folds that we have specified. So for this is where we start doing the fill in the blanks part. There is an existing sklearn function already that allows us to perform this cross-validation split, where we do the splitting of the dataset into our folds. However, in order to understand or better understand how we can do this, like the logic behind this function, we're going to do it from scratch. So we have the skeleton of the function. We have our function name, and then we're going to have our input, which is the data set, and the folds, which is how many divisions do we want for this data set. For this example, we're going to stick with 5 folds. And here, as you can see, we're creating an empty array or list to store our splits. And then we're going to create a copy of our data set so that we don't actually change our original data. And we still have that saved within a different variable. So for this, we're going to iterate through the range of folds, which is the input that we received, which is folds. Right. So inside our for loop, we're going to create a fold variable, which is a list. And in that list, we're going to add the data that we actually have from our dataset copy. So in order to do that, while we have created the fold list here, we're going to iterate through the entire dataset copy and then one by one input all of our datasets into that fold. So let's go ahead and do that. So basically what this code is doing right now is, while we haven't exceeded the fold size mentioned, which is over here, which is basically how many data samples we want in each like division, while that's not exceeded, we continue to do whatever we're doing here. Which is, so what we're doing now is creating an index to sort of give like a label for these data sets. So we can sort of count how many we're planning to put inside our fold. Then once we have our range, we can just append the division of our dataset copy based on the index that we provided. Right. So now that is us adding it in. Mhm. Yeah. Once we have that there, once we've added it into the fold, we can just remove the index because we don't want the same index to be kept as an actual column in the next few folds. Right. So once we have removed that, the this entire process goes on until we reach the needed amount of samples inside our fold. Then once that happens, we're going to save it into a new variable, this division of data samples. Then we can run that to sort of save our function, which we can then later use in the later processes. So after we split our data set, the next thing that we have to do is, of course, evaluate it. So in this part, that's what we're going to do. We're going to split our data set folds into tests and train in order to get the accuracies for each fold. So what we're doing right now is basically for train, we want to capture inside splits all of the data from the beginning up until the index J. And from here, it's going to be the index right after J up until the end of our split. Right. I hope everybody was able to write that. And then inside the train, since what we have is basically a list of lists, we want to aggregate that list of lists into one big list. So this is what we're doing here inside this for loop. Now, once we have our training and testing data, we want to sort of bring it back and from an array into a data frame. So this is what these lines of codes are doing. We're assigning back the columns for the necessary data and allowing it to become a data frame once more. So we can actually perform the necessary functions for the dataset. And then here, xtrain and ytrain, which is basically the process of us dividing it to attributes and labels, or features and the result. Now we're going to be comparing the performances of two models. So this is why we've elected to put this code here. We're looking into linear SVM models and the nonlinear SVM model, which is going to be defined through here. So once we have actually defined the model, we're going to fit, or we're going to begin the training process using the fit function. Now, an important thing to note when we're doing the fit function is we have to ensure that we're only using the data from our train section. We don't want to use data that is kept inside the test. Then once the fitting happens or the training happens, we also want to be able to see what results our model will return. So that's what we use for the YPRED, which is our prediction, our label or result predictions. Now, this is when we actually use the division of our test. So this is the test features that we want to get, and then that is what they're predicting. The model will be predicting its labels on. Then once we have that, we're going to add the results into, we're going to append the results into our results variable. Now we're going to be doing the same thing in our kernel model. So this is the nonlinear SVM model. Right. So once we have the code for our function, we can go ahead and load it in and save it into our environment. Now, after we have that, we're going ahead and finally evaluating the models that we have created. So here, as you can see, we're calling the k-fold CV method, which is the one that we have created over here. So that's the one that sort of creates our folds and then gets the accuracies for each one of them. Now, because this part is actually doing the training, which you can see here, it might take some time to run. So we'll give it a couple of seconds to continue running. Now, after this runs, ideally, we're going to be able to get our results and the fold size or the number of samples in each fold that we created. Now, as we showed earlier, what we have is this function, and what we want is the average score. So, of course, we're going to get a sort of aggregate of scores for each fold. So basically what we're going to do is sort of get the average of it. So we go ahead and run this. And as you can see, we now have the accuracies for each of the 5 different folds that we initialized, and as well as the average accuracy for this specific model. For this one, like it says, we can see that the results for the linear is much higher in terms of accuracy as compared to the kernel or the nonlinear support vector machine model. So now that we have this comparison, we're going to go ahead and properly compare them using what is called a z-score. So what is a z-score essentially? For a z-score, what we're going to do is use the accuracies, and rather than just comparing them manually by looking at the numbers, we're going to statistically compare them and see the standard deviation of each of these accuracy scores in comparison with each other. So there is already a standard values that we have for z-scores and testing the hypothesis, and this is what we're going to follow today. So first, again, we already have the variance function and the z-score function. We just need to code them into here. Right. So we have our variance here calculated. Now we just need to use the variance values in order to be able to calculate our final z-score. All right. So now we have that. We're just going to print whether or not the z-score exceeds our value, which is this. Considering we're looking at a 95% confidence level, we're going to be checking if our z-score is higher or lower than this standard value. Then we can go ahead and run that. So as you can see, the z-score comparison also shows supports the same answer we got when we were manually comparing the accuracies of both of our models. So here we saw that the linear SVM performs much better than the kernel or nonlinear SVM. And according to the standard z-scores, we're also able to see that, yes, the linear model is greater than the nonlinear model. Now, the reason we use specifically the absolute model, the z-score, rather than checking whether or not it's negative or positive, is we just want to focus on how far the variance of the accuracies are. So like how much each accuracies of how much the average accuracy of each fold varies when it comes to the individual folds. So we just want to see how big that distance is from the mean, which is why we're not looking at whether that distance is negative or positive. Now, we come to our final part, which is the improvement of our machine learning models. So again, there are many ways to be able to improve your machine learning models. As mentioned before, we have 4 main ways, but today we'll be focusing on the last 2, which is oversampling and ensemble methods using the random forest classifier. So here we're going to be checking our labels. For this one, we're going to see if the classes are equal or not. And as you can see, there's not an equal number of classes in terms of how many people survived and how many people died. So what we're going to do is sort of manipulate or add a few additions to this data set to make sure that our samples are equal and is representative. Now, it'll be up to you as you continue on different use cases and different projects to see whether or not you should be making each class equal. That depends on your research and whether or not you think this method is suitable for the use case. So we'll go ahead and first check the accuracies of our model when it comes to the data being in balance. So here, as you can see, rather than using the custom function that we created earlier, we're now using the standard function in the libraries of Sklearn, which is cross-validate. What it does is basically the same thing that we went through earlier when we were splitting the data set into folds and then getting the accuracies of each one. So as you can see, using this, we are able to get an accuracy of around 78%. Now, the differences between the 4 performance metrics we're looking at now is for accuracy, that's sort of just a general how much of the labels that we predicted were correct in all of our predictions. And when it comes to precision, what we're looking at is how much of the true labels that we're looking at were actually part of the true things that were part of the true labels that we are looking when it comes to the labels. And for recall, this one is more similar in the sense that out of all of the true labels, how much is it that we were able to predict correctly rather than just saying this is a false positive. So what we're looking at is 4 things: true positives, false positives, true negatives, and false negatives. So all of these are concerned with the accuracy, precision, and recall. Now, when it comes to the F1 score, that's when we want to sort of get an overall look on how precise and how much recall that the model has in general. So this sort of a mean between the precision and recall. So you can see overall it has around an 70+%, but we can still add a couple of improvements to that. So let's go through that by using the random oversample. We're having a sampling strategy of now we're going to be going through our entire data set and sort of using the random oversampler function to perform the necessary changes. And then once we did these changes, we can look at the effect of those changes onto the performance metrics we're looking at. And as you can see, there is a slight but still noticeable improvement on the general performance metrics that you're able to get. And yes, that is one way that you can improve your model using oversampling. If, however, this method was not suitable to your use case, you can also try to use the ensemble methods, among which is a random forest classifier. So again, as I previously mentioned, when it comes to ensemble methods, the general concept of it is using weak learners or a group of smaller weak learner models and using those to create predictions. And in the end, combining these predictions and aggregating them to make a prediction that is slightly less biased as it would. So let's go ahead and create and type in the random forest classifier. We'll give it around 100 small trees. Yes. Then again, it's going to perform the cross-validation on our data set. So as you can see, with the help of a random forest classifier, we were able to improve its performance up to 80% accuracy. So these are simply a couple of the basic functions that you can use when you're looking to work on or start on your machine learning projects. And there are many more methods that you can use when you want to explore different use cases and different projects. And you can learn through a lot of them by going through the Sklearn library or PyTorch and using whichever courses will be available to you at the time. So yes, that wraps up our quick look into model evaluation and improvement with the help of scikit-learn. If anybody has any further questions, I'm open to hearing from you guys. Okay, for Iman's question, that would depend on your use case, honestly. Accuracy is a good way to sort of get an overall performance of your model, but in some cases, accuracy will not show you the whole picture. So ideally, it would be better if you can look at other metrics. Like, again, we have our precision and recall. So in use cases where accuracy would not be sufficient, say in a medical use case, where we want to look at, say, how accurate is it when we're trying to predict whether or not a patient may or may not have cancer. So you can have like a high accuracy on this, but then the high accuracy is just it being able to predict whether the high accuracy just lies in the model being able to predict that this person does not have cancer. But that is not what we're looking at. And ideally, we'd want to look at how many people would or are likely to get cancer because we want that specific result as compared to just overall accuracy of the model. For students' data performance prediction, I suppose for this use case, you want to see how good students will perform. If your data set, I think, has the right amount of data, I think you can rely on accuracy for this one because it's not as sensitive to the negatives as I'd expect at least. I hope that helps clear things up a little, but yeah. Right. If anybody else has any further questions on machine learning models in general or just as a journey of a student, I'm open to answering them. All right, then, if there are no further questions from everybody, I think we can wrap it up for today. And I hope you guys will be able to enjoy the rest of the conferences and talks.
Thank you, Ma Althea. It was very interesting, and thank you for everyone for attending the tutorial. We'll have a break now, and then see you back here at 5:30.
All right, thank you so
Thank
much.
you all. You're welcome. Thank you.